Right, so I think we should get started in order to keep on time. So this morning, I think most of the talks are on whole molecules in Rydberg systems. It's my pleasure to introduce Tom Killian, who will be our first speaker. He's going to tell us about Rydberg atoms and synthetic dimensions. Thanks.
Great, thanks, James. Thank you all for coming this morning. I'd also like to express my thanks to the organizers of the workshop for their efforts in putting it together. It's really wonderful to gather here. So I'm going to talk about our experiments and our most recent results at Rice from our studies of Rydberg atoms and synthetic dimensions. You heard a little bit of this yesterday because this work is in collaboration with Barry Dunning at Rice and several graduate students. We also have a lot of theory support from Caden Hazard, and a lot of this was actually his original idea, so I have to give him a lot of credit. And Shuhei Yoshida and Jochen Bergdorfer from Vienna have also been very helpful on figuring out a lot of the properties of Rydberg atoms, which are critical for these experiments. So here's the outline. First, I'll describe what our Rydberg atom synthetic dimensions setup is, and present a realization of a superheder single particle Hamiltonian and topological edge states, which show the power, and has been a platform for us to sort of figure out all the different tools that are at our disposal, the limitations and the possibilities. And I'll talk about how we've measured the band structure of this Hamiltonian, and then some more recent results where we've extended coherence times and improved our state selective detection in the synthetic dimensions, and that's allowed us to study wave packet dynamics and to see the difference between bulk and edge states in the time domain, and then to study how, as we break a certain symmetry and we watch the edge protection get destroyed in this single particle Hamiltonian. And I'll say a few words about future directions as well. So a synthetic dimension is a degree of freedom that can be engineered to match the Hamiltonian of a particle moving in a real space dimension. And these synthetic dimensions are very powerful platforms for quantum simulation because of the amount of control that one has over all the parameters of the Hamiltonian traditionally, and they're very well, usually very well characterized. And this allows you to realize systems that may be very difficult or impossible to realize in real space. And these many experiments have been done on this idea and realizing interesting things like chiral edge states or synthetic fields. There are many different platforms. Here's a list from a review article from a few years ago. A lot of the early work was done in hyperfine states in atoms, where the hyperfine states were connected by Raman lasers. Here's a diagram from a very nice paper from a while ago. So that's an internal state. You can also do this with external states. So momentum states of atoms have been used for as a synthetic dimension, and also molecular states have been proposed at least, and then various ways to use photon modes as the underlying states for your synthetic dimension. Many other realizations, too many to list them all. So what I'll talk about today is a relatively newer idea to use the Rydberg states of atoms connected by millimeter waves. And the first time I saw this mentioned was in this review article, but it is very closely related to a proposal from Caden Hazard on using the molecular rotational states of molecules. And we first realized this experimentally. It was published last year. It's also got a very nice result just put on the archive relatively recently from Bruce Gadway and Jacob Covey on the same idea. So how does it really work? So you take a collection of Rydberg states. Here I'm showing a ladder of S and P states, and you identify some subset of them as the analogs of sites on a real lattice. And so a particle at a certain site in a synthetic dimension will correspond to the internal state of this atom being in a certain of these Rydberg states. Now, the tunneling between the levels is created by millimeter wave couplings between the levels. And you can set the rate of tunneling by the intensity and whatever the transition matrix element is. And the different sort of topological or geometric configuration of your synthetic space is set just by the way you connect all these different states. So you have a lot of flexibility in how you set that up. If all of your millimeter waves are on resonance, then you create degenerate states. And if you detune the millimeter waves, then you can create different chemical potentials in the synthetic space on each site. So you really have a lot of freedom here. So compared to other platforms for synthetic dimensions, there are several really nice things about Rydberg atoms. There are many states and relatively long lifetimes of these states. And that's long, at least compared to the type of coupling or tunneling that you can get between the states. And the coupling, as I said, is set by millimeter waves, and that's for reasonable Rydberg levels. The millimeter waves will be in the 1 to 100 gigahertz frequency range, where there's a really robust technical commercial products available for creating and driving those microwaves with great precision. So it's a relatively simple and robust system to connect up this Hamiltonian. And because of the large electronic matrix elements between Rydberg levels, it's easy to get Rabi frequencies and tunnelings on the order of 1 to 10 megahertz. And that, as I implied, is long compared to the lifetimes of the states, which can be many tens of microseconds. Another thing which I'll spend a bit of time talking about today is you can detect where your Rydberg atom is, or where your atom is in the synthetic dimension, with selective field ionization, and that can have essentially single site resolution within the synthetic dimension. So there are lots of different things that one can do. I showed a linear collection of states for a linear one-dimensional synthetic dimension, but by connecting up plaquettes, you can do higher dimensions. Or other topologies not easily accessible. Here's you can arrange some states into a Mobius strip. There's potential for Floquet drives. If you control the phases in a loop or plaquette, then you can create synthetic fields. You should be able to put the Jordan on. You can add dissipation, and if you choose the right states, it also should be possible to have localized many-body interactions if you can get multiple atoms into the system. And the way you get multiple atoms, and this is what the Gadway and Covey already demonstrated, and we're working towards it still, is to have atoms and optical tweezers, so one atom per tweezer. So in real space, they're relatively close, and you apply the same millimeter waves, and then it's like these particles are moving in the same synthetic space. So this is how you can get many particles in there, and this will get many-body physics, which might be more complicated than the single particle physics that we've demonstrated so far. There are lots of subtleties to think about here. I'd be happy to talk about that later. And so also you can do particle dynamics by putting particles in the system and then watching how the wave packets move around. So as we set the system up and wanted to explore its possibilities, we had to choose a nice system that we could use, one that we understood enough, but also had some interesting physics to try to show. And so we chose the SSH Hamiltonian. So that is a one-dimensional system. It's an analog of an electron hopping on a polyacetylene molecule with alternating strong and weak bonds. And so this is typically a finite lattice, and there are unit cells of two sites each. And so if there are n unit cells, then there are 2 n sites. And so you can label a sublattice A and B. And as I said, there's alternating weak and strong tunneling. Traditionally, there's no on-site potential. And this is a really nice model to do because it has interesting physics. In particular, it has topological order and a topologically protected edge state. And that edge state exists and is protected if you have a chiral symmetry. And so that chiral symmetry basically exists if in the Hamiltonian, there are only matrix elements connecting A to B sites and B to A sites. There are no elements connecting A to A or B to B. So that's why you have no on-site potential. And if you have this chiral symmetry, then I'll show you have a topology, you have an protected edge state. It's relatively simple to solve this for a number of states we have right now, which is 6. So you can put this Hamiltonian in a matrix into a Mathematica or some other system and solve for the eigenstates and evolution as well. So if we do that, we can look and see what are the energy levels the band structure is supposed to be in this Hamiltonian. Even with 6 levels, you can really see a band structure emerge. And here what's shown is the different eigenstates of that Hamiltonian, and the bars are showing how much amplitude of each state is composed on the different raw states of the synthetic space. So 1, 2, 3, 4, 5, 6 is 1, 2, 3, 4, 5, 6. So for example, this state is all in the middle states or the bulk, whereas these two states, which have energy equal to 0, have their population or their probability localized on the edge states. So these are the edge states with energy equal to 0, which show that you have this chiral symmetry, and they're robust to perturbations as long as you preserve that chiral symmetry. So I can change the amplitudes of connections and things like that. And these states at E equals 0 stay at E equals 0. And this is one of the many signatures of the SSH Hamiltonian when it's in this, what we call the topological configuration of weak connections to the edge state. If we change it so that we have strong connections to the edge state, and that's the trivial configuration, and there are no states that are localized on the edge, and there's no E equals 0 state. So these are the signatures we're going to look for in the band structure, but also in the dynamics. When we're in this topological state, we expect that if we create population in these edge states, it should stay in the edge states. If we create population initially in the bulk states, we expect it to rattle around in the bulk. So we'd like to see if we can see that dynamics as well. And if we can see all these signatures, then it's showing us that this synthetic dimension is a really platform is good, that we can realize all these different states with high fidelity. Okay, so what's the experimental details? We do our experiments with atomic strontium, typically with the 84 strontium. That's the easiest to work with to create cold gases. We don't really need dense gases in this respect because we're only doing single particle dynamics. But we do like it cold so they're not moving around too fast. And we put our sample into a 1064 nanometer optical trap, as I said, relatively low densities. And we do our experiment in a pulsed mode. And with one sample, we can actually run the experiment maybe 1,000 times, doing pulses in which we create just one Rydberg atom or 0 at a time. We don't want multiple atoms at this time because we wouldn't have a way of controlling their separation, and that would lead to Rydberg blockade during excitation, which could be interesting at some point. But right now, we keep it just one particle at a time, so we're just looking at the single particle Hamiltonian. The states that we choose are the triplet, at least for the first part of the talk, is triplet S1 and triplet P0 states. And we have single photon transitions from S to P, and we run from 57S up to the 59P state. So the triplet P0 is not degenerate, but the triplet S1, there are 3 magnetic sublevels. And we apply a 4 Gauss field that lifts the degeneracy of those states. And both for optical excitation and for the millimeter waves, we stay in the M equals 1 triplet S1 state. So we go from the M equals 1 triplet S1 to the M equals 0 triplet P0, M equals 1 triplet S1, and so on. And that's our system of 6 well-defined states. For band structure, we'll apply the microwaves, the millimeter waves, so that whatever the lattice is of synthetic dimension is there. And then we do optical excitation through 2 photon excitation from the ground state into the synthetic manifold. And I'll say a little bit more about how that works. For dynamics, we will we will have the millimeter waves off, and we'll excite to a bare Rydberg state, and then turn off the optical excitation, then turn on the millimeter waves, essentially quenching it into the appropriate synthetic dimension Hamiltonian, and then we'll watch the system evolve from it. So 2 different ways of doing the experiment. And the tunnelings can be up to 4. J can be up to 2 megahertz in the experiments that were shown. Okay, and for detecting the Rydberg atoms and detecting which state they're in, we use selective field ionization, where we, after an excitation, we hold, but in this case, we typically don't hold for very long after excitation. Then we'll apply an electric field ramp, and then the different Rydberg levels will ionize at a characteristic field. The electron in our case is detected towards an electron multiplier, allowing us to detect if a Rydberg atom was created with relatively high efficiency. And by looking at the field at which the electron is liberated, we can actually backtrack and say which Rydberg level the electron was in before it was ionized. So we could say which site was occupied in the lattice. Okay, so let's talk a little bit more about this probe. So this is the experiment where we look at the band structure. So we have the millimeter waves on, the lattice is created, and then we essentially inject the particle into this coupled 6-level manifold. Now it took me a while to sort of wrap my head around exactly what we're doing, because I can have the Rydberg, the excitation laser, tuned near any of these 6 states, and then I can tune around one of these states, and then see what happens. So if we tune to state number 3, so this triplet S1 state, and we tune our laser around that state, just a small amount, we get a signal here. So this is the number of Rydberg atoms as a function of detuning on the order of megahertz around the bare resonance frequency of the 58S triplet S1, or site number 3 in the lattice. And you can see we see structure that's split on the order of megahertz or so. The splitting is on the order of these tunneling rates in the lattice. And so what you're measuring when you excite to state 3 is the detuning of your laser from the bare energy is like measuring the energy in of your lattice state or in the band structure. And the intensity is the overlap of the state at that energy with the bare Rydberg state that your laser is tuned to. So essentially, as I tune over here to the left to, it looks like about 0.5 megahertz detune from 0, and I see a big resonance, I can see, well, in my synthetic dimension, there's a state at energy minus 0.5 megahertz, and the big intensity here says it's got a lot of overlap with state number 3, so in the bulk. If I tune near the middle, I can see there's a little bit of response there at energy equals 0, so I have a state at n equals 0, and it's got just a that state at a equals 0 has a very small overlap with state number 3, or the state in the bulk. So okay, so I build this up, and essentially these intensities match the So as I tune these different states, I'm looking at this state or this state or this state or this state. They're all at different energies in the synthetic dimension. And I'm looking at the different amplitudes of them with the different lattice sites. If I tune to a bare state that's going to correspond to the edge and do the same thing, the spectrum looks different. Now at E equals 0, I see a big response. Okay, that's my edge state. And there's a big intensity because at E equals 0, there's a big overlap with the bare edge state. So I see this big response. So essentially, wherever I tune, I'm still measuring the spectrum. I'm measuring one band structure for the synthetic dimension, but by tuning to the different bare levels, I'm looking and seeing, I'm able to map out how these different states in the synthetic lattice, I'm able to decompose them on the bare states. So if I combine all the different spectra, in this case, tuning to 57S, 58S, 59S, I get everything, all the energies all line up. So I measure the band structure that way. And by looking at which signals are strong and weak, I can decompose it back on the bare state. So if my ratio of the strong to the weak tunneling is relatively small, the levels are relatively close together in the synthetic dimension. So that's over here for low, J strong over J weak. And if I increase J strong over J weak, then the states spread out. So these are the bulk states that are tuning away from E equals 0. And they have high overlap with the bulk states, the levels in the center. And in the middle at E equals 0, these are the edge states with high overlap with the edge, and energy equals 0 as I change the couplings. So as I said, I've already walked through this decomposition, but by looking at the various intensities, when I tune to the different levels, I can really work out quantitatively the state decomposition, and nicely the ones at E equals 0 are really localized at the edge. And these strengths all follow what you get when you solve the Hamiltonian numerically and back out the states as well. So it all makes sense. And if I go to the trivial configuration with strong coupling to the edge states, then you see there's no state at E equals 0. All you see essentially is bulk states, as shown here in this diagram. So this was the first demonstration of we're realizing the Hamiltonian, everything seems to work well, and the system is robust, and we have a lot of control. So there, as I mentioned, lots of different things that we can do here. One of the first things we wanted to do is to explore whether we could look at particle dynamics. So what I showed you is the band structure that was in our first paper, and now our more recent results is trying to look at particle dynamics. So the way we do a dynamics experiment is we turn off the millimeter wave, which is essentially like making a very, very deep lattice in the synthetic space with no tunnel. So the states are very, very localized. And if I then promote an atom up into a Rydberg state, it's very localized in that one Rydberg state, localized in that one site of the lattice. Then I turn off the excitation, and these are just microsecond or so pulses. And then I turn on the millimeter waves, which creates the tunneling, or essentially makes the lattice shallower. So tunneling now is turned on, and then that'll start the dynamics going. And I can evolve it for some time, and then I can turn off the tunneling, and then I can do whatever diagnostics I want to do. And so, here's selective field ionization, and I'll focus on that a little bit more. So here's the selective field ionization that I can do. And as I ramp up the field, if I have a well-defined Rydberg state, all the signal will come at a well-defined electric field. But if I have some system that's spread over different states in the synthetic dimension, then when I ramp up the field, I'll see signal at different places corresponding to the different Rydberg states. And if I create a bulk state, then the population shows up in these states here, 59S, 58P, which turn out to correspond to the Rydberg states that are in the bulk. And if I tune my laser to an edge state, then most of the signal will show up over here to its 57S, which corresponds to I = 1. That was an edge state in the lattice. So you can kind of see it's this the probe is telling us what we want to see, but it's not great. It turns out for this S to P ladder, because of the quantum defects, I don't have single site resolution. I can't tell whether it's a 58S or 58P. They show up in the same space on the selective field ionization. So that's a little bit of a limitation. And we'll sort of transition and talk about some of the limitations that we saw in addition to that not having single site resolution in the S to P configuration. Other challenges that we've run into so far with this. I'd say the biggest one is AC start shifts. As you apply these tunnelings, we have to apply several hundred kilohertz to a megahertz kind of frequencies in order to really get the band structure split. And it turns out that creates AC start shifts on the order of that size because of connections, big contributions, connections outside of our synthetic dimension manifold. That's there's a lot of Rydberg states, which is good, but there's also a lot of Rydberg states, which is bad because your millimeter waves can couple you outside this manifold, maybe off resonance, and that creates complicated AC start shifts. So we have to characterize those all very carefully in order to determine how to get the millimeter wave on resonance. So that's definitely a complication. The hardware complexity starts to increase a little bit as we go to larger lattice sites. I'd like to go beyond 6 states. I'd like to get to 10 or 20 where we can really do plaquettes and loops and things like this. Decoherence is a bit of an issue here. At least with these S to P states, you could see as we increase the millimeter wave, you could see exciting to some states, the levels really are broadening here. So there's some decoherence coming on. I think it's the coupling to other levels is a big part of it, but we still haven't actually figured out all the decoherence. But with the S to P, we certainly saw some states only had microsecond level coherence times on these millimeter wave transitions. And that's really not good enough when you've only got megahertz type frequencies. And the decoherence would vary with microwave power. So somehow the coupling is hurting us. But also, as I mentioned, with the S to P, we only have two site resolution. So we were able to do nice work here, but we really want to do a little better. So what we transitioned to is a ladder of pure S states. So triplet S with 2 photon transitions. And again, we have the magnetic field applied so that it lifts the transition, and we're just going from M = 1 to M = 1 to M = 1. And in our system with the 2 photon transitions, we saw much longer coherence times. So now we have typically 30, 40, 50 microsecond coherence times with megahertz level Rabi frequencies. Just puts us in a much better position to have better resolution on the band structure, but it also means we have time to see dynamics on the system. And what also is nice is that now we really have single site resolution on the selective field ionization. The S states are now well resolved. So if we ramp up, I can see the 63S, 62, 61, 60, 59, and they're well separated. So all the data I'm going to show you is just doing a very simple, taking a window on these on selective field ionization to identify which state we're in. We could do much better than this by developing some sort of fitting procedure to really separate the levels better. We haven't done that yet. So I think we'll get much better resolution in the data I've just shown just with analysis. But already we can see a lot of things. Now, I haven't talked about it too much, but we probably are going to lose the localized interactions. We'll now have van der Waals interactions when we put atoms and tweezers next to each other with this state, so it won't be great for everything. So it's still a lot to develop. The van der Waals interactions are probably the same no matter which states the atoms are in. They're very similar, whereas the dipole sp and ps interactions are actually localized in space in the synthetics. Okay, so here's the first data on the dynamics. This is actually data over here. Really looks nice. So we have our 6 levels. We first optically excite to in this case, the 59s. So this is a state that's going to be in the bulk. And then we apply the millimeter waves to see the evolution. So this is now as a function of time. And this is the 58S state, the 59S state, the 60S, 61, 62, and 63, the relative population in these different states. So you can see right here at t equals 0, the 59S starts up near a relative population of 1, and everybody else starts at 0. So we start off localized in the 59S state. And then as time goes by on the microsecond time scale, there's fast oscillation between the 59S and the 60S. Get that? So that is the strong tunneling rate or the strong Rabi frequency. So you see oscillations between these strongly linked. And then on a longer time scale, in the order of 10 microseconds or so, you see tunneling out of this strongly coupled pair through to the other strongly coupled pair, where then it oscillates back and forth over there, and you see it go back and forth, but it stays within these 4 states that are in the bulk. So if we start off in the bulk, the system rattles around in the bulk states, but it never goes into the edge, or very little. So here we're seeing the characteristics of the SSH Hamiltonian, where we have the protected edge states and the bulk states are showing up in the dynamics as well. And we can look at our simple numerical modeling, look at time evolution as well, and put in the Rabi frequencies that we expect to have. And so the time dependence is naturally followed. But you can definitely see some decoherence showing up in here. Our model doesn't have that, so the model shows that the population the contrast should maintain longer. So there's a lot to still figure out. So what's giving rise to this decoherence, but it's pretty good, and we're pretty happy with that. Now, on a longer time scale, the system does lose its decoherence, but that's the decoherence for these oscillations between the internal states. But the protection to the edge state, that's much more robust, and that lasts longer, even well past when there's high contrast oscillations happening within the bulk state. Now, I should say that this graph here is showing the total population in all the Rydberg states. And so with these quantum numbers, we have around a 75 microsecond lifetime with black body radiation and with a natural decay. And so you can see on roughly that time scale, the total population is decaying away. So we do normalize all this data at all times. So this is always the relative population of what's remaining in these triplet S1 states. Okay, so that's the population in the bulk. What happens if we put the atom in the edge state to start with? So we excite to 58S, and then we turn on the millimeter waves. And so again, here's the 58 population, 59, 60, 61, 62, 63. So we start off with population highly localized on this edge state. And as time evolves, you can see that actually what happens is you tunnel from edge state to edge state. So the population goes down on this lower edge and comes up on the upper, and very little population in the bulk state. So this is also what you expect. We can do our numerical simulation to show that happens. And essentially with a finite with a finite ladder, you get a small energy splitting between the edge states. And that's why you get some tunneling from one edge to the other. As your lattice gets longer, your synthetic dimension gets longer, this tunneling rate would go down, get slower and slower and slower until eventually there's no tunneling and it's localized. And also the amplitude of this tunneling will go down if you detune some of these microwaves just a little bit. I'll show that, and the frequency would go up. So this was about as good, as close as we could get to thinking that all the millimeter waves are on resonance. Our simulation says that tunneling should still be lower. So perhaps the millimeter waves still aren't quite perfect, but this is the slowest edge-to-edge tunneling we can get. But this was one thing that I really wanted to see, because we sort of see this macroscopic tunneling from one edge state to the other. And again, it's a nice demonstration. We really can realize this Hamiltonian pretty clean. Okay, so other things we can look at is if I do detune this just a little bit, and I look at the population in the various states after about 20 microseconds, so that's well into the tunneling, you get the maximum tunneling from edge to edge when your detuning is 0. And as you detune away just a little bit, this is very sensitive. We're only detuning away a few 5 or 10 kilohertz, then the tunneling goes away and then stops. So it's very sensitive to resonance between these two levels to get this edge-to-edge tunneling. And you never really see much going up in the bulk on this small detuning range, just a few tens of kilohertz. Okay. Now, though, if I detune much further, now on a megahertz detuning, then I'm really breaking this chiral symmetry. And what I could look at is and see, have I broken my edge protection in this Hamiltonian? So we excite to the edge state here, and we do detunings on the order of megahertz, and we look very quickly in just a few microseconds. So there's no time for the edge-to-edge tunneling here. But what there is time for is there a time for population to leak into the bulk if we break this chiral symmetry and we lose the edge protection. So here is the population in the initial state. So it starts at population of 1 at t equals 0, but after a few microseconds, population has evolved. If I have 0 detuning, population stays in the edge state. But if I detune away 500 kilohertz or so, then I lose population from the edge, and it shows up in the bulk. So this is looking at the 59S, the first bulk, and the 60S, the next bulk state. And you can see as I lose population from this edge, it leaks into the bulk when my detuning is on the order of 500 kilohertz or so. If I detune further, and again, I don't think I said this, I'm changing the detuning of this, the connection to this edge. Okay. So if I detune that far enough, then the edge state just stays completely isolated and there's no connection to the bulk. So that's what happens if I detune really far, population stays in the bulk. But if the detuning is on the order of a few hundred kilohertz, so on the order of the Rabi frequencies, then I break this chiral symmetry because I essentially have chemical potentials on the different states. And now I tunnel from the edge states into the bulk state, and I've lost this edge state. Okay, so this is a good time for me to wrap up. I just want to take a minute or so to point out the really nice work done in the Covey and the Gadway lab at Illinois Urbana-Champaign, although Gadway is moving to Penn State. So they were able to realize optical tweezers, and they just had pairs of atoms close to each other. So really just think of, you just think of these two atoms and their tweezers, and they connected 4 states within one principal quantum number by using different angular momentum states, and they could form a plaquette by closing the loop, and also they could phase lock the synthesizers to apply relative phases to these drives, and that actually introduced the effects kind of like a synthetic field. And over here, just single particle dynamics, depending upon and this is the population in 0 state, I believe that's where they started with. And depending upon the relative phases of these millimeter waves, they could get different dynamics. They could actually turn off some of the tunneling of the different phases. And then when they get 2 particles close to each other, then the dynamics are affected. So the interactions are starting to see interacting particles in this synthetic space as well. So they have a theory that matches this. And so there's 2 states, but now they could go on to more states as well. And there are predictions from Caden Hazard, a paper that he did a couple of years ago to predict lots of interesting states like bound states, string states, or if there's a one-dimensional array, you can get particles bound together that will tunnel together, or in a 2-dimensional array, you can get sort of a membrane state that tunnels together. So really rich physics to study here in the many body realizations as well. Okay, so I'll wrap up. So we've demonstrated the Rydberg synthetic dimensions is a good platform for quantum simulation, and we've shown so far in my laboratory a single particle realization, but the Covey and Gadway groups are realized multiple particles. And our first demonstration was the SFH model, topological edge states, where we've shown band structure and dynamics. We've looked at, well, there's still a lot to study on the coherence times and robustness of the different states. And we're also working on putting optical lattices together so we can go to multi-particle systems. And also we really want to move beyond 6 states to 10 or 20 would be really nice to realize all the richness. So thank the funding agencies. AFOSR has funded this, the National Science Foundation in the US. And then my collaborators, experimental side, graduate students, some now postdoc, Neil Yuan are the current students on experiment, and Joe Whalen is now the Naval Observatory in Washington, D.C. And of course, theory collaborators, and Robert Randall is also graduate student help some of these experiments. So thank you very much for your attention.
Some time for questions.
You mentioned at the beginning about disorder. Can you put phase noise or something on some of these fields to make some disorder or couple with some other particular precipitation? Can you?
Yeah. So one of the most obvious things is the potential to kind of you can get a disorder in the chemical balance. But yes, you can. We have some ideas for how to participation in. You can use another way to connect out of one state out of the lattice to some other state, which maybe you optically connect to a ground state or something like that. So dissipation could be very good. So non-Hertzian Hamiltonians, I think, will be very interesting with these systems. So at least those are a couple of different ways of disorder. There could be more.
It's a very nice result. So when you detect, you field analysis, you get the coefficient square of this contribution. Is it possible to get the phase or the sign?
I don't know. I have to think of some way of projecting on some other state to get some interference. There might be maybe some kind of rotation you could do in the synthetic space. I haven't thought about that a lot, but that's those are the kind of things I think about to see if I would probably try to figure out. My guess is I'd probably have to try to apply some sort of an operation to project it on some other state and then see how that turns out to be able to backtrack what the phases are. That'd be my guess. So maybe possible, but I haven't thought too much about it.
Yeah. How accurately do you have to tune the route?
Yeah, so the Rabi, it's relatively forgiving to the Rabi frequencies, at least for these experiments, because that preserves the chiral symmetry. So if my Rabi frequencies aren't right, I might get the lines a little bit broadened, but the dynamics would overall be the same. But those are actually easy to get right, because I can look just 2 particles at a time and look at the Rabi frequencies and get those really, really accurately. It's the detunings that are hard. So you've got to get the detunings kind of on a 10 kilohertz level. And I think that's probably the best, as good as we're able to do in these, and we can see all of this dynamics. So that's sort of better than 10% of the weak Rabi frequency is when we get the detunings right at that level, then all band structure looks right. If we don't get that, then the band structure is asymmetric. You have levels all over the place. And at first, when you're trying to get it right, you just have this mush. You try to figure out where it is, and as you start to get it right, then the band structure emerges, and then you're trying to balance the amplitudes of the 2 levels and narrowing the band structure. And those are the kind of signatures you look at to see if you've got the tuning right.
So before you measure, do you actually get an optimize for it?
Yes, we typically do. Yeah.
If you look at one end of when you have the edge state, it looks like this sort of EIT scenario. I wonder what role the other photon are playing in the fields. Have you looked at just sort of applying, two fields and then adding in some of the other end and seeing how that
coupled or decoupled additional millimeter waves? Certainly we do when we do.
Yes, the event state, you've got a weak thing on the edge, and then a strong thing, because exactly on the EIT scenario.
Yeah.
And I wonder how much role is those other people playing in that case, so if I start out in the bottom one, then what's the different dynamics where I guess.
Yeah,
that's like
yeah, it's an interesting way to think about it. We certainly we build up the system and we're aligning it. We start with just simply EIT, we make that look right.
Yeah.
And so there are a few things that happen as you add more transitions. The most immediate is as you add these transitions, it basically starts to shift these. So you have to go back and then retune and make sure things look reasonable. So we'll apply all these transitions and not connect it to here and try to get a nice looking EIT. And then as we apply things, when you start to get extra features on the system, the most dramatic is when you when you apply this edge state down, this last one down here, now you get tunneling all the way from edge to edge. For example. Right. That's one example of what happens when you start to add more complexity.
I think there is one more question, maybe quick.
Because the voltage difference is like the difference from the
sorry, I didn't say that. One of the really important things is that each one of these transitions it has a unique energy. So we have to apply multiple different frequency tone for each transition. So we have independent control of the tunnelings and the detunings for all these transitions. But they're all on the same time. Yeah.
Okay, let's thank Tom again. I think we can continue on.
The pointer's fading a little bit. You might want to use it for the pointer. Feel the microphone. Angles.